Hi, welcome back to the session on thermal physics. So before we stopped temporarily, we have been discussing about the entropy and the second law of thermodynamics as a part of our discussion of module number 4. So far we have seen the concept of entropy starting from the Clausius theorem, and we discussed about the entropy in reversible processes as well as irreversible processes. We could prove the Clausius mathematical statement of the second law. Its reversible part was named as the Clausius theorem, and the irreversible part was named as the Clausius inequality. Thereafter, we started with obtaining a general expression for the entropy change for the ideal gas system. We obtained 3 expressions for the entropy change of an ideal gas in terms of P and T, in terms of the V and T, and finally in terms of P and V. So these were the expressions for entropy change, which was in general applicable for any thermodynamic process undergone by an ideal gas system. Remember, the system we have fixed, which is the ideal gas system, and the expressions were general. General means applicable for any kind of process that is undergone by an ideal gas system. So let me summarize the equations that we have derived so far. The equations that we have derived. So first equation was change in entropy. Remember, in all these cases we derived general expressions for the change in entropy during a process. So delta S, I am writing change in entropy as delta S, which is equal to S2 minus S1, okay, where S2 is the final entropy of the system and S1 is the initial entropy of the system. Okay, so delta S is equal to one of the equation was CV log T2 by T1 plus NR log, all these are natural logarithms, V2 by V1. That is one of the equations. So this is the expression for the entropy change of an ideal gas system in terms of the initial and final values of the temperature and that of the volume. Okay. See, now equation number 2. All this equation gives you entropy change of the ideal gas system in a process. That's equal to Cp log T2 by T1, Cp log T2 by T1 minus, that is a notable difference, minus NR log P2 by P1. So this equation gives the entropy change of an ideal gas system in terms of the temperatures and the pressures. Okay, means no reference to the volume. Then the third equation that we have derived was delta S equals Cp log V2 by V1 plus Cv log P2 by P1. Okay, so this expression is free of the temperature. Now what we will do in this session, we will be deriving or we will be developing expressions for the change in entropy of an ideal gas system in different processes, in specific processes. These 3 equations what you have written here or derived earlier are applicable for in general, okay, for any process, depending on what data is available with us, whether you have the temperature data and volume data, or you have got the temperature data and the pressure data, or you have some information about the volume and pressure of the system, then we will be selecting one out of these three equations to calculate the change in entropy in the respective cases. Okay, but in special cases, in special processes, say for example, what are the different processes, thermodynamic processes that we usually talk about? One is an isothermal process. So the various standard thermodynamic processes may be either isothermal process, it can be isobaric process, it can be isobaric process, it can be isochoric process, or it can be adiabatic process. These are the standard thermodynamic process that usually is undergone by any thermodynamic system. So what we will do is that we will be we will be developing the entropy change equations from 1, 2, 3, which are general expressions, to applicable for these unique processes separately. So you will see that this equation will be getting reduced to simpler versions. Okay, that we will do. So we will start by one. We will first see how equations 1, 2, 3 will transform in the case of isothermal process. It's quite simple. It's just a matter of mathematical manipulation. So we'll see that. Okay, so let me go to the next slide. So let me do one thing. Let me take these equations also along with me, so that it will be easy for me. Just a moment. Yeah, here I have got the equation that we are derived now. So let me keep it as a reference for us. Let that be here, right? So we will be discussing, as I told you, first the isothermal process. So you know, isothermal process means that the temperature T is a constant, T equal to a constant. Okay, or in our special case, we can say that T1 is equal to T2. For the system in question, T1 equal to T2 always. So let's see how the equation 1, 2, 3 are getting modified. So when you look at equation number on the right side, general expressions for the entropy change on the right side, you will see that only equation 1 and 2 are having dependence on temperature, right? So T1, T2 equation. So we have to modify only equation number 1 and 2. So for isothermal process, equation number 1 will be getting modified. So how it will be getting modified? Delta S is equal to, okay, so what about the first term? It will be Cv log T2 by T1, but T2 and T1 are equal. Okay, so what will be log of T2 by T1? It will be log of 1. And you know, log of 1, natural logarithm of 1, that is equal to 0. Log 1 equal to 0. So what will happen is that this term will be getting vanished, and what only remains is the second term. So it gets reduced to very simple equation. So delta S becomes, in that case, delta S is equal to simply the second term, nr log V2 by V1. Hope you understood it. It's quite simple. So that is our final result. So if the process is an isothermal one, then the change in entropy of an ideal gas system can be directly calculated as delta S equal to nr log V2 by V1, right? So that is one expression. Now there is a possibility for obtaining another expression. So this equation is in terms of volume, right? volume, initial and final volume, V2 and V1 are there. Now it is given that temperature is given a constant. So if temperature is a constant, what can vary? Both the pressure and volume can vary. So you have a chance to obtain another expression for delta S in terms of the pressure. So let's see how to do that. For that, you can depend upon equation number 2. So equation number 2 on the right side will be of use to us. So you know what to do. The same thing you are going to do here. So equation number 2 will give you, what is equation number 2 giving you? Again, once again, delta S is equal to, see, the same manner, the first term will be getting vanished, because here T2 by T1 will be equal to log of 1, that is equal to 0. So what remains is only the second term in equation number 2. So what is that equal to? That is minus nr log P2 by P1, minus nr log P2 by P1. Okay, so this is another expression. So let me call this one as equation number 4, and this is equation number what? Or 4a. I'm calling it 4a, and this is what? 4b. You will see this is 4a and 4b. Okay, that is the two equations that we needed. Is it not quite simple? Now one thing more. Okay, see, just look at equation number 4a and 4b. One gives you the change in entropy of an ideal gas system in an isothermal process in terms of volume changes, and here it is in terms of what? Pressure changes. So depending on whether you are given, or whether you know the pressure change or you know the volume change in a particular case or a problem, you can apply one of these, right? Otherwise also you can just look at how these expressions, so there is 1 plus nr log of this one, and here it is minus nr log of this one. So you can, it's always good that how you can think why it is there is a negative sign and all here in another way also. Even though the general expression have been derived, you can always think why there is a negative sign here. So let me give you a hint here. Say for example, it's only to discuss or only to understand this equation better. We are discussing about an ideal gas system. So the equation of state is always applicable. So what is the equation of state for an ideal gas system? That is PV equal to nRT, right? Okay. And you know that for an isothermal process, T is equal to a constant. So T equal to a constant. So from that, N is constant, R is constant, and T is also a constant in this particular case. So what do you get? You get PV equal to simply what? A constant. It's not our, just what you call Boyle's law and all. So, right, PV equal to a constant. And PV equal to a constant for an isothermal process means that P is inversely proportional to V. Is it not? P is inversely proportional to V. So what does it mean? It means that if you take, P2 by P1, is it not? If you take P2 by P1, that will be equal to what? V1 by V2. P2 by P1 will be equal to what? V1 by V2. Is it not? It won't be equal to V2 by V1. So it will be just the reciprocal. So P2 by P1 will be equal to V1 by V2. So this expression tells you, why there is a negative sign between this and this. In 4a and 4b there is a change in the polarity. I think it's clear to you. Why? Because if you take log of P2 by P1, log of P2 by P1, you can do in any way. Okay, it's equal to log of, instead of P2 by P1, what you should substitute? You should substitute V1 by V2. So it will be equal to log of V1 by V2, right? Log of V1 by V2. Now can't you just write this one as minus log of V2 by V1? Minus log of V2 by V1? Simple, because I have inverted. I have changed the numerator and denominator, and you can just replace with a negative sign. That is simple logic. Minus log of V2 by V1. Or, is not what you can see that from this relation and this relation, can you say that log P2 by P1 is equal to minus of log V2 by V1? Or log V2 by V1 is not here in equation 4a can be replaced with minus log P2 by P1. So these are all simple mathematical tricks that you can, if you can remember it, it will be quite easy for you to deal with. Or remembering the equation also is a matter. Hope that is okay with you. So it's up to you whether to memorize this equation or to memorize this equation. What I suggest to you is that better you memorize, better you memorize equation 1, 2, 3, which we already have derived. You memorize equation 1, 2, 3 without error, plus or minus error, and from equation 1, 2, 3, depending on the situation or depending on the problem that you have to face, following what we are doing right now, you will be able to derive or obtain specific equations that is applicable for isothermal, isobaric, isochoric or adiabatic process. That is what I suggest. Do not just burden your memory. Do not burden yourself by memorizing each and every equation. That won't help you anywhere. Okay, see that you try to memorize general expressions as far as possible, and that you do it well, so that it doesn't go wrong either in terms of the variables or in terms of the sign. It should not be mistaken or confused. Okay, so memorize the minimum number of equations as far as possible and understand for what case it is applicable. We are doing all these equations only for ideal gas system. Okay, it's a very special case of ideal gas system, and mostly we will be dealing with what ideal gas systems in our preliminary studies, right? So memorize equation 1, 2, 3 for sure, and understand what to do when when a requirement comes in. That is what will be useful for you. So I think we will be just moving on to the same manner. We can just move on to case number 2, which can be an isobaric process, you say. So let me do one thing. Let me take equation 1, 2, 3 along with me. Okay. So let me take equation 1, 2, 3 also along with me. Yeah. So we have equation 1, 2, 3 here as a reference, right? That is where we will begin with our cases. So as you see, our equation is, or our case is isobaric. So when you say isobaric, you know that it means P equal to a constant. P equal to a constant, or P1 equal to P2 in our case. So now you know what to do. Even I need not explain it much. So which all equations will be modified now? So you can see that equation number 1 has got dependence on temperature and volume only, so it's of no use for us, this special case. So we will be modifying in this case equation 2 and 3. They will be of use for us. So how equation number 2 will be getting modified? So equation 2 gets modified as you can see delta S is equal to, directly you can write it, delta S equal to simply Cp log T2 by T1. Cp log T2 by T1. Cp log T2 by T1. And you know, this thing will be vanishing. What will it be? Because P2 equal to P1. So log of P2 by P1 will be equal to log of 1, which is equal to 0. So this term will be getting vanished. So this is the expression that we are going to get. Quite simple, is it not? Now, the same manner you can rewrite equation number 3 also. What is that? It tells you that delta S is equal to simply, here also the second term will be vanishing, right? So here also you can see this term is vanished because this P2 by P1. So it will be equal to again Cp log V2 by V1. V2 by V1. So you note this one. Didn't you see that both here it is Cp, here also it is Cp itself, right? And here it is log T2 by T1, here also log V2 by V1. Can you presume why there is no change in sign as in the previous case? Earlier it was a plus NR and there was a minus NR, but here it is both positive. Why it is so? Because, you know, once again you can logically argue that it should be so. PV equal to nRT, PV equal to nRT. We are talking about an isobaric process, so NR is constant and P is also constant. So given that, you can see that the relation is V proportional to T, volume proportional to T. That is a very well-known relationship for an isobaric process of ideal gas system. So V proportional to T means what? V1 by V2 or V2 by V1 will be always equal to what? T2 by T1. So there is no need of any inversion or anything. So wherever you see V2 by V1 or T2 by T1, you can replace with the other one without any change in the sign. So here T2 by T1 is there, just you replace T2 by T1 with what? V2 by V1 without any changes elsewhere. So these equations are also applicable for isobaric process depending on whether you know the temperature data or you know the volume data. Okay, I think it is clear to you. Now let's move on to the same manner. You can move on to the third case. Which all things? We have discussed isothermal, isobaric. Now what is left with is what? Isochoric, the process where the volume remains constant. So let's move on to the next one and let's bring in the equation that we need. So this is the reference equation. So these are the three equations that I suggest you to please memorize it. Okay, so practice deriving these three expressions. That will be a best way to memorize this equation together, right? See, so as such, let's begin what we have been doing. So we just wrote see, isochoric. Isochoric means V equal to a constant. So let's be systematic in that case. So it means that V1 is equal to V2. So you know what will be the fate of equation number 1, 2, 3 here. So which all equations will be of use for us? Whichever equation is having volume. So equation number 1 will be used by us, and equation number 3 will be of use to us. You can see there is a sort of symmetry in all our discussions. So it will be a pair of 2, 2, 2 equations, right? So what will be the fate of equation number 1? So let me write what is equation number 1 giving you? V1 equal to V2. So automatically this second term will be 0, because log V2 by V1 will be equal to log of 1 is equal to 0. So what is delta S? So delta S will be equal to, in an isochoric process, it will be equal to CV simply log T2 by T1. CV log T2 by T1. Is it okay? Fine. Now another 3 will give you another expression in terms of the pressure. What is that? That is delta S is equal to, yeah, here also the volume expression will be getting 0. No? So this is 0. This term is 0. So it will be equal to simply CV log, and that's also quite interesting, CV log P2 by P1. Please do verify this one. You can see that here also CV, here also CV. This is T2 by T1, here also P2 by P1. Why should it be so? The reason is well and clear. Why? It's once again PV equal to nRT, right? It's not. N and R are constant, and we are discussing isochoric process where V is also constant. So what is left out? Only the variables are pressure and temperature. So can you see that pressure is directly proportional to temperature? So it means that P2 by P1 will be equal to T2 by T1 directly. So you can see that you can directly replace T2 by T1 with the P2 by P1. Okay, so these expressions will be helping you to calculate the entropy change of an ideal gas in isochoric process. And remember, okay, these are all expressions. Now one thing, let me invite your attention to. You can see in all these equation 1, 2, 3 that we have derived, for memory's sake, you note one thing. All the ratios that we are using here is 2 by 1. That is one thing to be noted. It all will, you always look at the expressions and try to find out the way in which they are written, so that it will be easy for you to recall all these equations whenever demand arises. Okay, should never have an doubt whether it was 1 by 2 or 2 by 1. Remember, we have derived the expression in such a way that the right side is always final quantity by initial quantity. So there is no doubt there. Okay, then you need to remember only the sign and the quantities involved. So hope that it won't be a problem for you if you are systematic enough, right? Fine. Now let me go to what is the process which is remaining. The process which remains is adiabatic process, and hope you remember already we have discussed about the entropy change in an adiabatic process. Anyway, let me tell you once again that. So hope you remember we are actually discussing about the reversible processes, right? Okay, reversible processes, okay, for an ideal gas system. And hope you remember, in reversible adiabatic processes, in reversible adiabatic processes, this already we have established adiabatic processes. Delta S, do you remember what is the value of delta S? In reversible adiabatic process, delta S is always equal to 0. Change in entropy is always equal to 0. What does it mean? S2 minus S1 equal to 0 means S2 equal to S1, or S initial equal to S final. What do you call such processes as? We call such processes by the name isentropic process. We have introduced this concept earlier too. Isentropic processes. So I told you the best example of an isentropic process in nature is what? reversible adiabatic process. Okay, a word of caution. Remember, if the process is adiabatic but not reversible, means in irreversible adiabatic process, remember the change in entropy is not positive. Okay, in irreversible adiabatic process, remember delta S is not equal to 0, instead it is positive, that is delta S is what? Greater than 0. Okay, so this I repeat time and again. Delta, whenever you are asked to comment on what is the nature of entropy change in an adiabatic process, you should be very, very cautious. The adiabatic process can be either reversible or irreversible. In the case of reversible adiabatic process, the word reversible is something very, very important. In the case of reversible adiabatic process, there is no heat exchange. Okay, there is no heat exchange happening with the system. There are no losses elsewhere. Okay, and it is happening quite slowly. In that idealized special case, only the entropy change delta S equal to 0, or only that type of process is an isentropic process. Even an adiabatic process which is not reversible or which is irreversible, the delta S is not 0, delta S is always positive, and always remember the delta S will be, okay, is not, these are all, we are talking about isolated systems. Okay, delta S is either 0 or greater than 0 for an isolated system. Okay, so remember I am using the word isolated system. Okay, and since it is isolated system, that is why we are talking about adiabatic case where dq is equal to 0, right? So that is something important. So a reversible conclusion of our session is, in a reversible adiabatic process, that change in entropy is 0, or it's an best example of isentropic process. Okay, so I think it's enough regarding the topic entropy change of an ideal gas. In your syllabus, it will be given entropy of an ideal gas. Remember, always instead of entropy, what will be calculating will be the entropy change. Okay, change in entropy will be of what is defined in thermodynamics. Okay, so just revise all these topics. It will be of use to you in solving problems. We'll be doing some problems also in the coming sessions. Okay, thank you.